Thanks everyone for relocating to the room for the afternoon talks. So yeah, I will present a little bit a new concept that we're developing at CSCS to like move up containers as what we call first-class HPC elements from the, because until now we feel that we have been using containers in HPC, but they're kind of a separate entity. You know, like there's something maybe on top of the rest of the HPC infrastructure. They're not really well integrated, and in some cases, like the rest of the HPC components and tools might or might not want to play nice with containers. So we're trying, and it doesn't make life easy for users as well. So we're trying to evolve on these kind of usage scenarios. So as you might have heard this week, one of the big news is from CSCS is the ramp up into production of Alps, our next generation research infrastructure based on a CRAE-X system. Here's a picture of our data center. It's meant to, as our director likes to remind, it's not a single computer, it's not a supercomputer, or even less so of a traditional HPC system. It is meant to be as a research infrastructure. So a general purpose resource. It's going to be a one hardware-based infrastructure, but with many uses. It's not going to be vertically integrated with one single software stack for one single user community. It will be dedicated to many purposes. And one of the key enablers of these of this role, of this purpose, is the vCluster technology, also developed by CSCS. We have these versatile software-defined clusters where we can sort of partition the machines, partition the infrastructure into subsets for specific tenants with custom settings for each of them. And all of this is managed through infrastructure as code approaches. So here is a diagram that allows you to that kind of expresses this idea that Alps will be really a foundational infrastructure on top of which we can instance multiple platforms and different clusters for different user communities, projects. We're going to have like the traditional HPC platform, the role that is now covered by Pittsdane, machine learning, weather and climate, and collaboration with like material science and other stuff. And these are not intended to be like physical individual clusters. Like this is all software defined and can be remapped and reconfigured very flexibly and very elastically. Hence the way Alps brings together cloud and HPC. And yeah, the system has got, even though it's not fully developed, fully deployed yet, we still got some good results in this ISC edition of the top 500 in HPCG, number 6 and number 5. So we have a very capable and very powerful machine. And within this model, in this perspective, we are switching from Pittsdane to Alps. We are taking the chance of rethinking on a lot of different levels how do we operate, how we provision, and how we use an HPC research infrastructure. So there is the level of the vCluster technology at the level of infrastructure, and how we also instance these platforms and these vClusters. But another level where we are thinking of evolving our practices is to leverage containers in order to manage user environments. So basically, the user environment comes from a container, and every time that the users run, they are into a container, whether they know this or not. And we know this brings a lot of advantages, both for us as HPC providers and for the user. So one of the biggest one is to decouple the user environments from system components. So that every time that, for example, there is a maintenance which updates the underlying software system stack, your applications don't break, and you don't, and we or you, for example, and we don't spend several weeks in troubleshooting and fixing all the applications. There is isolation of software version and dependencies. This is something that is very convenient for users because they can get whatever dependency and whatever package they want with the version they want. Consistency of the environment, easy to deploy, compatibility by moving images, depending. Your mileage may vary. We heard about different opinions and perspectives on compatibility this morning. And they're also moving everything to containers allows for flexibility of experimentation, because it means that if you're trying something new, you don't necessarily have to fiddle in with your production stack. So the problem, this is nice, but there is a problem that there is an underlying complexity and friction in turning containers into usable computing environments. Like downloading an image is very easy. It's just your pull commands, singularity pull, source pull, you can do this in a one-liner. You can get your image, but transforming that image into something that you can actually use, you're going to have to link several bind mounts in there. You might have to want to customize environment variables. You want a different, maybe an entry, you want to use the entry point, maybe you don't want to use the entry point, and a bunch of other settings where you want to use OCI hooks and whatnot. So basically, for real world use cases, in order to launch a container in an HPC system, it's like this amount of command line, like 5 or 6, and I see Shane nodding. So this is the problem that we have to overcome. And our goal is to, this happens because, as I said before, containers are not really integrated into the HPC system. The rest of the HPC ecosystem doesn't really recognize or plays along with containers and the container tools. So we want to increase this integration between the containers and the HPC infrastructure. And that's where the ideas of containers as first-class HPC elements come in, so that containers become a foundational element, a foundational object. They are treated somewhat equally or as peers by other HPC components, and they can sort of build up on the strengths of each other. So we set ourselves 5 principles that underlie this concept. First one should be ease of use, both for users and for operators of the HPC infrastructure. It should remove complexity as much as possible in the sense of how it is operated, how it is launched, and what happens inside from getting from a container image to a running container environment. Must ensure predictable operation, seamless integration with the rest of the HPC components, and minimal learning curve for the users. It should be very similar. It should be the environment should feel very familiar. This is a diagram of an architecture as we currently envision it, implementing this concept of containers of first-class elements. So the most relevant pieces are the ones connected to the user and to the Slurm workload manager. We're currently looking at a plugin to sort of act as an interface for the users, and a declarative file, which we call an environment definition file, which will basically hide all the different and possibly complex steps and interaction with the rest of the ecosystem. So basically, the user only speaks with a convenient interface to the workload manager, and under the hood, we figure out where and how we need to pull an image, rebuild an image, how it interfaces with the identity provider, which kind of resources we need to inject. So for example, we have vendor hardware specs like the CDI that we heard this morning in container hooks. So this is kind of the general idea. And we have started experimenting and implementing this with a Pathfinder implementation. So as I mentioned, the most important element in this Pathfinder implementation is this concept of the environment definition file. which basically is meant to be a comprehensive blueprint detailing all the properties of the computing environment, of this container-based computing environment that the user wants to have. So within this user, this file captures all the container customization. As I said, it's declarative and it's composable, and allows to abstract away and automate all the container tools. It is based on the TOML format. You might be already familiar with it. It's a fairly popular configuration file format, easy to read, easy to write, and also already in use by other container tools, like Podman uses TOML for their configuration formats. I think it's also used by Singularity and Obtainer in some for some files, and it's very easy to find and integrate parsers for that. Just a quick tour over the features that we have right now in the EDF. As I said, we give the possibility of defining a base environment, so you can just reference a previous one and build on top of a previous environment. So you inherit settings, and this is one of the way. This is the way I mentioned that it's composable. You can compose environments by relying on previous settings. You can specify images. It can be a Docker reference. It can be a Squash file already in the file system. In this case, it references the NVIDIA HPC toolkit from NGC. We use arrays, TOML arrays, to define sets of bind mounts into the container. So it's very convenient because you can kind of leverage the multi-line feature and the multi-line comprehension of the file format. So it's kind of easier than saying -- mount or -v or in the command line. We also use a TOML table for environment variables, so that you can add, you can modify, you can unset variables into the container. And we also have a section for OCI-like annotations, where the main purpose of this is to add metadata so that other tools or other bits related to the containers know what to do. We mainly use this to enable or control hooks. For example, here are two examples. We can enable the CXI, which is the HP provider for the Slingshot interconnect, and the Nickel plugin. Just a quick tour over other features of the Pathfinder implementation. Our current proof of concept is based on the Pixis and Enroute, or two tools, open source tools developed by NVIDIA. We added the parsing for the EDF. I'm running a little bit low on time, so I will skip over most of these details. This is a quick example for showing like a remote debugging workflow. So in this example, in the first line, I'm inheriting a base environment for PyTorch, and I'm just saying, so it's basically the listing is an EDF, that is a file that I may want to write. I want to enable I want to inherit the base settings for PyTorch, and I also want to start the hook for a hook to set up an SSH connection into the container and enable a public key that I might have already loaded into the system. And then I use this with a single command line option, specifying my TOML file. And so what happens is that the container runtime will read the specification, call the SSH hook, which will start a daemon and enable my connection. So then once I started the container, I can go back to my laptop and start up VS Code and have a remote connection and edit the code on my laptop and have it run live on the HPC system. So all this, it was just a single command. A couple of other use cases where some other colleagues have used this to do training of ForecastNet. It's a data-driven weather forecasting models based on based on deep learning. So this gives you a way of how even a relatively simple EDF can enable a very complicated use case. And this is, for example, another example of inheriting system defaults for a machine learning cluster. So on the top is there are the settings which might be defined by a system administrator to preserve bash history or consistency of the /tmp file system. And so everything that the user needs to do is the bottom side. So I want to just change my image, and all the rest I will take the defaults recommended by the system administrator. Yeah, so this is the conclusion. The containers as first-class object approach addresses the current need that we have for software environments, provides isolation and reproducibility, and we think it provides a more accessible, modular, and extensible way to use containers in HPC. And we have published a paper about our first experiences on Alps at CUG, so it will be publicly available from the CUG website in a few months. Or if you're interested, you can just reach out to me. Thank you.